Hello, everyone, and thanks so much for having me here. I'm going to talk about the paper we wrote in collaboration with Harun Yusuf, Anya Piotrowska, Sanket Kanyalkar, Sergio Delgado, Andrew Miller, and Sarah Meiklejohn from various universities and research institutions. And in this paper, we analyzed basically the level of privacy provided in the Lightning Network. So before diving into the details, I would like to give a brief introduction by mentioning the two main issues that are currently inherent in cryptocurrencies that Lightning aim to solve. The first one is the privacy issue, and it's well established by now that Bitcoin doesn't provide much anonymity, and there are many papers that have attacked Bitcoin's anonymity, even with coins that were designed with privacy as its main design, there were like flaws there. So lack of privacy is a well-established problem in cryptocurrencies. The second one is the lack of scalability, like especially with Bitcoin, where currently it can support around 7 transactions per second. And if you compare this number with Visa's network, which can compare up to a couple of thousands, you can see that these two networks are incomparable, and there definitely needs to be, and for example, Bitcoin cannot be used for everyday payments, for micro payments, because of this very low scalability. So Lightning Network was proposed in 2016 and its main focus was to tackle these two issues that were in Bitcoin. So to give a very brief introduction, what happens in the Lightning Network, we have two users, let's call them Alice and Bob, who create, in order to create the Lightning channel between them, they create a funding transaction, which is broadcasted into the blockchain. This funding transaction determines the initial balances of these two users in this channel. What happens in practice is that only one of the users funds this transaction nowadays, and the money in the beginning belongs to the user that actually opened this transaction. But for sake of generality, let's assume that initially two users contribute. After creating this transaction, and you have the initial balances, the user can update those balances constantly by creating commitment transactions that are shared amongst them without the usage of the blockchain. So these updates of the channels are instant. After updating the channels several times, they can do it indefinitely. The users can choose to close the channel by broadcasting and closing transaction, which is again broadcasted to the blockchain. So basically the main issue here is that the blockchain is only used twice in order to accommodate many transactions between two users. Let's assume that Alice has opened her channels and she wants to forward the payment to Bob. Alice does not need to have a direct channel with Bob, because using HTLCs, Lightning can accommodate payments between nodes that do not share a channel. This happens by Alice forwarding a payment through intermediate nodes who are responsible for forwarding her payment on her behalf. HTLCs make sure that either all of the channels in the path are updated or none of them is. The main privacy properties of Lightning that we focused on, and they're the main properties that exist, is first of all, the balances of the channel should remain hidden. Only the users that participate in this channel should know their balances. When a node, the second property is that when a node participates in a payment, when a node does not participate in the payment, the node must not learn nothing about this payment at all, not even that it happened. But even if the node participates in the payment, it should not learn much information. It should only learn who is the successor node and who is the predecessor node of this particular payment. It should not learn, for example, who is the original sender and receiver. So these are the three main properties that we analyzed. In terms of the first property and the balance discovery, we implemented an attack that was already proposed in literature in order to see how possible it is. So in the attack over here, an attacker aims to identify the balances between Alice and Bob by doing the following. Without Bob ever creating an invoice, the attacker forwards a payment to Alice and he waits for a reply. If Alice says that the hash you provided in the payment is unknown, it means that the payment actually reached Bob. And if it reached Bob, it means that Alice had enough balance to accommodate this payment. So using this information, the attacker uses binary search and tweaks constantly his payment in order to identify what is exactly the value of what are exactly the balances between Alice and Bob. Once we implemented this attack, the main outcomes were the following. Almost more than 90% of the channels we attempted to attack failed, and this was mainly due to two errors we constantly received: unknown next peer and channel disabled. But not only we were not able to attack most of the channels, but we were not able to connect with the majority of the nodes. The main reasons were that the nodes were publishing a false IP address. They were not online, or they were publishing wrong ports. So even if their IP was correct, their ports that were responsible for communicating with Lightning were closed. So these were the two main outcomes that showed the poor usability of Lightning that made it even harder to perform a running attack on a live network. And the channels that we were able to actually attack, 45% of them were one-sided. Only one party had all the money. We extended this attack with our novel approach that didn't rely anymore on error messages coming from other nodes. This feature is very important because our attack, our extension is able to work even if the LND client or the C-Lightning client updates and it does not give error messages anymore. So we no longer rely on error messages, or as we call them, an oracle. So in this situation, an attacker has two nodes and he forwards a payment and he is the sender and the receiver. So basically the intuition here is that when he forwards a payment from his first node, if the second node sees the payment, it means that Alice had enough money to accommodate the payment. And if the second node does not receive the payment, it means otherwise. Again, using a binary search, you can infer the exact balance between Alice and Paul. So in terms of the second privacy property, which says that an external node should learn nothing about payments that he's not involved in, we did the following. Imagine an adversary being able to run the balance discovery attacks I mentioned earlier at two particular different timestamps. And let's call the first snapshot he obtains from timestamp 1, snapshot 1, and the other one, snapshot 2. What the attacker can do then is compare the balances he inferred from the different snapshots and infer information on what happened in between. Basically, a change of balance means that the payment happened in this particular channel. The closer the snapshots are to each other, the most effective the attack. But on the other hand, of course, it's more expensive. We analyze in the paper in detail the trade-off between these two features and how an actual low budget attacker can perform a very efficient attack. In terms of the third property, and in particular the on-path discovery attack, in order to do it, we had first to create our own Lightning Network simulator to obtain very crucial information that are not public. In order to create a simulator, we have two different types of parameters. The first type of parameter is the node and network parameters. These parameters were not estimated, but were rather ground truth knowledge. And we obtained this knowledge, this information, by running an LND client and constantly scraping every 1 hour the network. We obtained information about the network topology, the capacities of the channel, the fees that nodes were charging, etc. We were also able to infer the geolocation of the nodes because this was very important on estimating the TCP delays between nodes based on this geolocation. The second type of parameters we used were the payment parameters. So far we know exactly how the network looks, who is connected with whom, with what channels, etc. But we had to estimate, to simulate the way people behave, the way people perform payments. And in order to do that, the first step was to categorize the users in 3 different types: the merchants, the routers, and the regular users. The merchants, the intuition behind this categorization is that most of the payment will originate from regular users who want to buy stuff from Lightning. So the main receivers of Lightning payments are the merchants, because these nodes have an incentive to get paid because they actually offer goods in using Lightning. So we parameterize these two parameters, the sending ratios and the receiving ratios of each categories as S of X and R of X. The total volume of the payment in the Lightning network was estimated using LNBig's estimation, which at the time of their writing controlled over 40% of the total network. So actually their estimation was very credible. The values of the individual payments were estimated using some kind of a power law distribution estimator, which basically said the bigger nodes, the most wealthy nodes, are the ones that are going to perform the most expensive payments. And this theory is backed by already by literature that has proven that even the Ethereum and the Bitcoin ecosystem follow the power law distribution. Actually, payments happen from the most wealthy clusters of addresses. So we assume that the same happened in Lightning as well. The main outcome of the simulator, the main reason we created the simulator, was to extract some conclusion about the behavior of Lightning. And the most important conclusion is this particular graph, which basically shows how dominant the path lengths are in the payments. So basically, what's the probability of a particular, of a random payment to have a particular path length? And we're going to see later why path lengths are so important. So to get back to the privacy property, in order to argue about our last privacy property, we created basically a game. And we said an intermediate node that's participating in a payment according to Lightning should know nothing more, but rather the predecessor and the successor node. But this is really the case. So the game is as follows. Our adversary is an intermediate node. His goal is to find the sender. Let's focus on the sender for now. His strategy is super simple. He will always guess that the sender is the node behind him, the predecessor node. The threat model here says that our adversary needs to keep his channels balanced. He should not keep all the money or have the other counterparty keep all the money for him. So the question is here, when the adversary is an intermediate node and he guesses that the sender is the predecessor node, how often is he right? Well, when the path is of length 3, he's always right because there's no other intermediate node. And as we saw in the previous graph, paths of length 3 are the most common ones. So already you can see that this strategy is effective. But this can be extended to more than one hop payments, because even if there are 2 hops in between a payment, there is a chance that our adversary is the first hop. So yeah, the predecessor node will be the sender. But how often is our adversary right? If you think 50%, well, that's not exactly the case in every case, but it depends, as we're going to see. And this can be extended to multi-hop. No matter how many hops are between the sender and the receiver, there is always a chance that our adversary is going to be the first hop, hence he will always be right in his strategy. So if we add up all these different scenarios, we're going to formulate the probability of the advantage of the adversary. So the first factor of our probabilities is what's the probability of a path being of a particular length. And this is directly drawn from the measurement we did earlier. The second part says, okay, my length is L. What's the probability of my adversary being the first hop? So drawn from the graph, the probability of a path being of length 3 varies from 30 to 40% according to different simulation parameters. So in terms of the second factor, the worst case scenario is that our adversary is always wrong, which means that although he's in the path, he's never the first hop. And this is the worst case scenario. It's pretty unrealistic. But there's also another case scenario. I wouldn't call it the best case scenario, but it's just a scenario that a path forms a clique, which means that if there are X hops, the probability of me being the first one is 1 over X. So it's equally probable to be in every position of the hop. We calculated these probabilities, and if we focus for a particular simulation over here, the lower bound probability of being correct for an adversary is more than 30%, but the maximum, the upper bound is more than 70%. So as you can see, although our strategy was very simple, it's actually very effective. So this is the way we tackled all the 3 properties, and we analyzed how much they were true. So if you have any questions, please feel free to ask. I would love to discuss.
Okay. Thanks a lot, Georgios. I think we have time for one question.
Yeah, if I may. Do you actually have any mitigation strategies in mind?
There are mitigations for several attacks. So one example would be for the balance discovery attack, for example. In order for the attack to be effective, you need to make multiple payments, because you will never, most of the case, you won't be lucky and directly find the balance, but you're going to use the binary search, as I said. So you're going to try multiple times. So a denial of service mechanism could prevent perhaps something like that, and basically reject payments that are that look like a binary search attack. In terms of the path discovery attack, the main problem here is that when a client chooses the path, it is driven by the optimization factor of paying the less fees. And this, because of the network topology, most of the times, as we saw, the path will be very small, will be like a length of equals 3. If the path was estimated using other optimizations, like for example, we want big paths in order to avoid this kind of attacks, this could also be a mitigation.